Hello, everyone, and thanks for tuning in to listen to this talk. I hope everyone has had a great summit experience so far. My name is Alex Coca, and I work as a research engineer for Seldon IO in London. At Seldon, we're passionate about helping companies bring their models to production with as minimal effort as possible, whilst also giving stakeholders a range of tools that they can use to monitor their model performance and to understand their models better. We think this is essential for the safe and responsible deployment of AI in the years to come. So part of our time is spent developing an open source library for model explanation called Alibi Explain. Since most explanations are expensive to compute, we needed a scalable and fast framework for distributed computing to power our library. So this is how we started working with Ray. Before I start, I'd like to acknowledge the contribution of my colleague Rafael for this work, as well as the support of Clive, Alejandro, and the wider Seldon team, and DigitalOcean for providing the computes to do this work. Last but not least, I'd like to acknowledge the insight and contribution of Bill and Ed from AnyScale. So without any further ado, I'd like to delve into my presentation. And there's two parts to it. First, I'll explain to you what a black box model is, how can we explain it, and why is it necessary to distribute the computation of model explanations. And second, I'll show you how one can leverage Ray in order to speed up the task of explaining an entire data set, and briefly discuss what insights we can get from it. So what is a black box model? You can think of a black box model as a complex function whose operation on a given input is unknown. We can pass an input to it, x, and we can read its output, y hat. But we usually don't know anything about how x is transformed into y hat. This is usually the case in production, where you have an API that you can query with your data, and you get a response back. The input could be, for example, an ultrasound image or data about a mortgage applicant, and the output can be a diagnosis or a decision on whether to allow a person to access a mortgage or not. So in such critical situations, we'd really like to probe these black boxes and understand the way it thinks, understand how it makes decisions. So how can we do this? What does it mean to really explain or probe these black boxes? So, for example, if we productionize a cat classifier, we might be interested in finding a subset of pixels that with high probability make our input a cat in the eyes of our model. So the subset of pixels is known as an anchor. And you can read more about this algorithm in the paper cited or our Alibi documentation. Another way to explain a model is to search for an input that differs from our original input as little as possible, yet yields a desired prediction. As an example, you can see on the left a digit that was correctly classified by a convolutional neural network. And on the right, I'm showing that changing that image ever so slightly can lead the model to predict its digit 5. And this type of explanation is called a counterfactual. Yet another way to do this is to attribute the difference between a model prediction and a base value, for example, the average prediction over a data set, to some input features. So for example, we have a classifier that takes a person's age, body mass index, blood pressure, and sex, and outputs a mortality risk for that person. Assume that a person was predicted a risk of 0.4 when the average risk in the population they're part of is 0.1. So we'd like to understand the 0.3 difference. You can see on the slide that features such as age, the blood pressure, or the body mass index increase the risk of that person dying, whereas the fact that the person is a female actually decreases the risk. So unfortunately, computing these numbers is hard. These attributions have exponential computational complexity. So to give you a sense for why we need Ray when we want to compute a lot of these model output explanations, I'm going to briefly digress and explain to you how a SHAP values is computed. So meet Alex, the CEO of Noodles.oi. It's the end of the quarter, and it seems they did pretty well. So he's super, super grateful for his employees' hard work and would like to share the profit with everyone in a fair manner proportional to their contribution. At a quarterly meeting, he presents the methodology that is going to guide the bonus scheme going forward. So he denotes by F the set of all the employees in the company, 5 in this case, and by 2 to the power of F, all the teams of any size that can be formed with his 5 employees. So to calculate an employee's contribution, for example, Abby's, Alex first makes all teams that do not contain Abby, gets them to work for a while, measures the profit, assuming he has enough time and this is all possible, and then adds Abby back to every single team and measures the profit again. He takes the difference, averages everything out, and this gives him an indication of how Abby has contributed to the big money that they gathered this quarter. Note that this requires enumeration of all possible teams of all sizes, and this is exponential in the number of employees in the company. So therefore, you may say, well, it only works for startups. But the same methodology really is applied for attributing the difference between a model output and a baseline value to the set of input features of a machine learning model. Translating this equation to machine learning language, the profit is just what our model outputs, whereas the teams represent subsets of input features. The problem is that we can't simply exclude features from the model input, usually, that just breaks our code. So what we need to do is to use an auxiliary data set so we replace and estimate the effect of missing features. So we already had to make an exponential number of calls to get the model output to calculate our values. But we need to do actually even more than that. There's also linear factoring involved. So whilst these methods to approximate these quantities exist, they're still very expensive. So explaining a large number of predictions is very expensive on a single CPU. So how can Ray help us speed up? Let me describe a practical task that we worked on. So we took a simple model, a logistic regression on the adult dataset, and proceeded to explain 205,060 predictions from a test set. Each prediction predicts whether an individual will make an income over $50,000 or not based on some data about them. We use the kernel SHAP algorithm, which is a way to approximate the SHAP values that I've just described. It's an implementation by Scott Lumberg and colleagues, and we built on the SHAP library. Note that each prediction is explained independently of all others, so the problem really lends itself nicely to parallelization. But running this task sequentially on a single CPU took us roughly half an hour, and this is even a simple task, so we really wanted to improve on it. So how do we implement this? One thing we really care in our open source library is having simple user interfaces. And this is what I particularly liked about working with Ray, its simplicity. In addition, its actor computation model integrated super nicely with our library as Alshred. So what we originally had in our library was the kernel SHAP explainer, which needed to know about the predictor and optionally about the features that go into it, what it outputs, and what kind of model it is. So the only change we had to make in order to enable parallel computation with Ray was to add a dictionary, and this dictionary would be a vehicle for the user to specify how many CPUs they have available on for this task. And optionally, they could also specify a mini batch size that controls how many of these instances are explained by the same CPU at one time. So what happens under the hood? Well, to start with, we had the fifth step that needed to prepare some data for our underlying calculation. So it was really easy to actually, instead of delegating the task to an object that did the calculation, as I've just shown here, it was really easy to create a distributed explainer object that took that original object that we already delegated the task to, along with its arguments and keyword arguments, and use that object to distribute the task. So the way we did this was simply to create a parallel pool. And as you see, here we just initialize Ray and create the parallel pool. And the pool creation has two very simple steps. First, we apply the remote decorator functionally because we just have the object and it's just the easiest way to do so, to create some actor handles. And then we just instantiate our explainer in each of the worker processes and create a pool with the actors. And this is all. When the user calls our API with a dataset they wish to explain, the get explanation method of this object gets called. And this takes the data set, it splits it into individual instances or perhaps mini batches, and then submits these individual mini batches or instances to the pool and returns the results at the end. So you can see that our target function for the pool is very simple and just calls the actor method that knows how to explain an instance. And this is all, really. And from a user perspective, all they need to do is to load their data and their model to tell us how many CPUs they want to use, fit the explainer, and explain it. It's just their workflow from before, but now many times faster. So just how fast we managed to get this thing? Well, you can see here some results. And we ran this task on a machine from DigitalOcean with 32 virtual CPUs, and it's a compute optimized machine and a dedicated one. So you can see a nice and linear almost increase up to 16 up to 16 workers, which is a nearly linear improvement because these are, let's go to the previous slide. So all the user needs to do is to load the data and their model, instantiate the explainer, tell us how many CPUs they want to use, and magically the computation gets distributed. So just how fast would this be? You can see here some results that we calculated by taking this code on a DigitalOcean machine with 32 virtual CPUs. And we represent the results on a logarithmic y-axis. You can see that up to 16 workers, we could get a nice, nearly linear improvement. But because our task is CPU bound, beyond we get much smaller improvements. Hyperthreading doesn't really help with our CPU bound work. So even so, we run our task in just over 2 minutes compared to approximately half an hour, which is really about 14 times faster. We try different batch sizes to ensure that each worker gets enough work in a call and ensure that the overhead of distributing the task isn't much greater than the task execution time. You may be thinking, surely there's a lot more work to take this to a cluster, but in reality, there are only a few extra steps we took to achieve this. You need to set up your cluster first. So I had to do this on my own because I was working with DigitalOcean. But you can use cloud providers such as AWS or Azure, you name it. The Ray guys have got you covered as the library offers a number of cluster launchers that you can use together with the Ray CLI to get you up and running quickly. After you've downloaded your configuration and built your image, you're ready to go. All you need to do is set up your Ray cluster. So I'm just going to take you very quickly through how we did this. You may know that a Ray cluster consists of array head node and worker nodes. We configured both of these as deployments, which are resources capable of scaling the image that you want to run on in Kubernetes. So to scale things, simply we increase the number of replicas. But you should know that in general, if you use Ray for this task and you expect good performance from it, or container needs to access a shared memory volume. This is more relevant for complex workloads where the actors perhaps need to talk to one another, but I thought it was nonetheless worth mentioning. So you can see here that we request 4 CPUs for each replica. So there are about 56 virtual CPUs running this task. And as I said, the head node is configured in the same way, except that there's a single replica because we only have one head node. So you notice that we also run ray start in order to initialize ray on each node. And this is no secret. It's available in the documentation. At this stage, you might be thinking, okay, so what about the script? Does that need to be changed a lot? And the answer is no. All you need to do is to pass the ray init, the address equals auto input, and this will take care of it. And this is really as little work as you need to do up to this point. And to take the script that I've just shown and upload to a cluster, we need to do a bit of work first. So we need to tell Kubernetes about our resources and the fact that it needs to provision them. And we use kubectl commands to do so, and specifically the apply command. In general, you can also use the ray CLI to achieve the same outcomes. After this step, we need to understand, okay, what's the name of my ray head node? So we get the name of that specific pod and copy our script to it. It's as simple as that, copy operation. And then we use kubectl exec to run a command on the head node. We know it's main now, so we know where to execute that command. And finally, we copy back our results. And it is as simple as that. In terms of results, we had really good success. The best average runtime, we run this run 5 times, was just under 1 minute, which is about 30 times faster. And we can see here on this graph that batching hurts performance a little. But as I said before, our explainer isn't really benefiting from taking those mini batches as input. It just increases the task runtime linearly. So what could be happening perhaps is that due to longer task running times and then be many less tasks to schedule as a whole, there could be less, only a few tasks left to run at the end, and some workers that are idle. So we're not making very efficient use of our cluster, but we haven't really dug into why this is the case. So now imagine a different use case. You're part of a team of data scientists that all develop models and want to explain them. And it would be quite painful if every single data scientist had to kind of replicate the workflow that I've just described. So ideally, these data scientists would also want their results quickly so that they can do their development. And you go and ask your boss what to do about it. And they say, oh, I have this spare Kubernetes cluster you can use. And if you're that data scientist, I've got a solution for you, because you can use ray-serve to get up and running in no time. So how can you do this? Well, there are 3 main steps to use ray-serve to deploy the same tasks that I've described. First, we need to create a request handler. We need to create endpoints and backends, and we need to distribute the requests. Arguably, the first 2 steps are what we care about the most. So in this case, we coded the kernel SHAP model, which is our request handler, which takes our predictor and the arguments for the explainer constructor and the fit step that I've mentioned, and we just instantiate and fit our explainer. That's it. The next step is to have a call method that extracts the input from a request, casts it to the type that the explainer needs, and calls the explainer. And for people like me who don't know much about Flask, this was really nice and convenient to set up. In some cases, if our model benefits from batching, Ray allows this functionality very simply. And the way we'd achieve this in this case is to override the call method, decorate it with the accept batch decorator, and make sure it handles a list of requests as opposed to a single request. And that's all we need to do. Okay, the second step is to create an endpoint. And you can see that this is relatively easy to achieve. We need to give the endpoint a name. We need to tell it what backends it needs to connect to. And then we need to tell it about the application route. And as soon as that's complete, we can create our backend. Our backend can be created with some nice and simple to use Ray utilities. We have the create backend function that we just need to call, and we need to pass the backend name so that the endpoint knows about its backend. And we need to pass, of course, our request handler to it. And we have the update backend config method that can allow us to update the backend anytime we want in production. So I use it in this case to change the batch size as I run these experiments. So at the script level, it's also very easy. You just need to run through these steps in sequence and call serve.init. And that's it, as easy as 1 and 2. And in Kubernetes world, you need to connect to the cluster just as we did before, and just make sure that serve can actually accept requests from other machines, which is why we have the HTTP host argument to serve.init. And you also need to find out the host for your array head node, which you can do with a simple Python code. Note that in order to really make this available to a team, one would also need to set up an ingress controller on the cluster so that you can actually connect to your cluster from the outside world. And this is the last step that you really need to do so your whole team could actually benefit from this. We use the same commands as before, the kubectl commands, to take the script on a Kubernetes cluster and execute it. And you can see that for the one node, so this isn't a Kubernetes cluster, it's just one machine that I've used, we have a runtime of just under 2 minutes, so about 15 times faster. And for the Kubernetes cluster, we achieve a runtime of just 61 seconds, which is 28 times faster. Note that the maximum resource allocation was 56 virtual CPUs. And for batching, we observe the same behavior as before. Note that this is a really really simple way to speed things up and for data scientists to explain their model predictions. So they'll thank you for it. So now the question comes, why bother? Why do we need to speed up this task? So, okay, you can see in this image that explaining many predictions allows us to aggregate feature effects at the individual level in order to obtain a global view of model behavior. So for instance, in the image on the slide, you can see that, for example, race and work class don't influence the odds of being predicted a income of over $50,000 that much. And this is, indicated at the very minimum that our classifier is not racially biased. A slightly more granular view of the same data we can actually have because we've created these explanations for each and every prediction. So we can see, for example, that a capital gain can have both a positive and a negative effect on the prediction of an income over $50,000. And that for some individuals who don't really have capital gain, the feature doesn't really impact the outcome that much. So this is the kind of insight you'd never get from a traditional tree-based model. So kernel SHAP allows us to do this for every type of model, but it is expensive to run. And due to Ray, we can actually offer data scientists and stakeholders the ability to do these things at a much, much larger scale, much, much faster. So now time for some very quick takeaways. I'm going to be brief. We all have a mandate to deploy robust and fair AI. And perhaps black box explanation feature along this journey. And as I demonstrated, Ray tremendously boosts the speed of execution of this task. So the data scientists now have a handle on perhaps identifying if their classifiers are fair or if they have certain biases that they don't know about. So if you're interested in the code that we use to run these tasks, you can find it on my GitHub. And if you want to know more about explanations and see the distributed SHAP in a library, you can go to GitHub and look at seldon.io/alibi for more. Thank you very much for your time, and I'm now open for your questions.